Hello everyone, welcome to my channel. This is Vijay Lakshmi. Today I'm going to discuss about undecidability. So before starting this, we know what actually is an algorithm is. It is a step-by-step procedure to solve a given problem. So the procedure will be having a finite sequence of instructions which has to be executed, and then once it completes the task, the algorithm terminates. So the same way, even we have a Turing machine. So here the Turing machine also performs certain tasks and it will halt. So here we say that a problem is said to be decidable if we can always construct a corresponding algorithm that can answer the problem correctly. It means that like how an algorithm will solve a task and stops the same way, the Turing machine also has to give the solution. Okay, and it has to it may run into a finite state, or it might run into an infinite state, or it may simply continuously gets looped. That is, a problem is said to be decidable if we can construct a Turing machine which will halt in finite amount of time for every input and gives answer as yes or no. Okay, and a decidable problem as an algorithm to determine the answer for a given input. So here the Turing machine will execute certain set of instructions. It may accept the string or it might reject the string. That is, it may accept the string and halt, or it might reject the string and halt. So here that is what called as a decidable language. For any language, if there exists an algorithm to solve a problem, okay, then if it accepts that language and stops, means the Turing machine is performing some operation. Or else the Turing machine may reject that language and it may halt and it may stop. Even that also can be accepted. So here, for example, consider here equivalence of two regular languages. Given two regular languages, if there is an algorithm and Turing machine to decide whether two regular languages are equal or not. So we can make use of a Turing machine to decide whether two regular languages are equal or not. So here we know that already in order to say certain languages are regular, we say that it should be closed under union, concatenation, clean star, like that. So here if any two languages you can combine, okay, and if there exists an algorithm to identify that the two languages are equal, means then we say that the Turing machine accepts that language and it halts. Otherwise it will reject and halt, or else it will enter into an infinite loop. So any three cases can happen. So that is nothing but we call it as a decidable. Decidable means there exists an algorithm which gives us an answer either yes or no. So that is called as the decidable. Undecidable means we will not get the answer at all. We cannot predict what will be the answer. So next, seeing here decidable. So problem in decidable, if a Turing machine exists that can solve the problem in a finite amount of time. Undecidable means what? Turing machine that can solve the problem for all inputs, and they cannot solve it in a finite amount of time. So any decidable language means there exists an algorithm to solve that problem. So it can be acceptable, or if it is non-Turing acceptable language, there does not exist an algorithm, but anyhow we can find the solution for like Hamilton cycles or graph coloring problems and all. No, there does not exist a definite algorithm, but using that we can find some solutions. Such kind of problems are called as non-Turing acceptable languages. Okay. And the next very important question in this fifth module is the recursively enumerable languages. So here a language L is recursively enumerable or Turing recognizable if there is a Turing machine M such that language of Turing machine should be equal to some language L. So this language L, a language L is decidable if there is a Turing machine M such that L of M, language of machine, should be equal to L and M halts on every input. It means this Turing machine, given some string S, it should accept, it is performing some task T1, it is accepting that it is performing some task on the input using Turing machine, it is accepting, or else the Turing machine will, for that string, it will accept that input and it will not accept that input, it will reject. Okay, anything may happen. So that is nothing but we call it as a recursively enabled language. So the language is recursively enabled if and only if there exists a Turing mission M such that that language L should be equal to Turing mission language T of M. Okay, so that's what here also we have to say that to accept some string, it might enter into an accept state by accepting the string, or it might reject the string. Okay guys, so the same thing will be repeated if the string, that is this yes, does not belongs to this language means. Okay, if it does not belongs to this language means it will reject. If the string whatever you have given, it belongs to some language L means, then it is accepted. So that is the meaning of the first statement given. A language L is recursively enumerable if it is accepted by the Turing machine. Okay guys, so just in the external exam you have to write this diagram and you have to explain what actually is enabled languages are. So here what we have to understand, a language, a mission may accept a language or it may reject a language. So the output of the mission may accept or reject. This problem is also called as a membership problem, and all such problems will always have two answers, that is yes or no, that is accept or reject, or finite or infinite. Such kind of problems are called as decision problems. So whenever we have two decisions, they are called as what? Decidable languages or decision problems. Sorry, DE, decision problems. DECISION, decision problems. So these kind of questions you will get for short answers. And also we know that recursively enabled languages are closed under intersection, concatenation and clean star. Okay, one example you have to write. Suppose that M1 and M2 accept the recursively enabled languages. That is, L1 is one language to accept the strings ending with AB, and L2 is another language to accept the strings ending with BA. So we need to show that if W is in our new language, so it will be accepted. The new string is what? It should be L1 intersection L2 or L1 union L2. If we run these languages on the mission M1 and M2, on both the Turing missions M1 and M2, so that Turing missions may accept that language or it might reject that language and enter into a halt. So Turing on a set of all Turing missions is countable. All the Turing missions are countable. Therefore set of recursively enabled languages is also countable. Okay guys. Next important question here is it's a full theory only. So non-deterministic polynomial problems, that is NP problems. So here we have two types of problems, that is P class problems and NP class problems. P class problems means the problems which can be solved in a polynomial time. Okay, where an algorithm exists and they can be solved in a polynomial time. And NP problems means these are a little bit hard, we say that, and it takes more time to solve the problems, and they take exponential time to solve, to find the solution. So they take exponential time in order to solve some problems. So such kind of problems are called as non-deterministic polynomial problems. So we can't predict what time it will take. So it would be like something O n factorial or something larger than that. So such kind of problems which takes a non-polynomial time during its runtime to solve a problem, they are called as NP problems. Example is your Sudoku game. So here anyhow we are going to get a solution for the Sudoku game, but we don't have a definite algorithm which runs in a polynomial time. So it will take exponential time to solve the problem, but anyhow we are going to get the solution for that problem. Coming for NP complete problems, here we can solve the problems in two ways, as I said, that is you can solve in polynomial time or in exponential time. Suppose if there exists a problem, there is a solution for the problem and it can be solved in exponential time. They are nothing but the NP complete problems, we say. So these problems are that are present in both NP and NP hard classes, and that is NP complete problems can be verified in polynomial time, and any NP can be reduced to this polynomial time. It means that These problems are giving us some solution, but they are taking NP time to solve the problem. So if a polynomial time algorithm exists for any of these type of problems, means then all problems in NP can be polynomial time solvable. There are many problems which are NP complete. So if for any one problem, if you find the solution, means that same thing can be applied for all other kinds of problems. Like we have a Hamilton cycle, graph coloring problems, etc. They are all our NP complete problems. So if you are able to solve a single problem, the same logic can be applied for the other remaining problems also to solve in a polynomial time. Okay, so coming for the definition of NP completeness, a language M is NP complete if it satisfies two conditions. That is, that language M is in NP. It means that it should be NP complete, and every A in NP, every problem in NP is polynomial time reducible to M. Every solution, whatever is given in NP, it should be polynomial time reducible. It should not be an exponential time. If you are able to reduce any one algorithm here, that can be applied for the other algorithms. For example, see here classes of P and NP, NP complete problems. Example, where it takes where no polynomial time. It means that it is taking NP non-polynomial time to solve the problem, like Hamilton cycle, or determining whether a Boolean formula is satisfactory, or NP hard problems like Hamilton cycle, sum of subsets, knapsack problem, traveling salesman problem. All these are NP hard problems. So here these problems are not polynomial time solvable. They are exponential time solvable, but there exists a solution, but there does not exist a definite algorithm to solve in a polynomial time. So that's what the second point in the previous slide is telling, that for any of the one problem, if you find the solution, it can be applied for the remaining problems also. So here P means here that is polynomial time solvable, and NP hard means it's undecidable problems, and that is there does not exist a definite algorithm to solve the problems. So here coming for NP complete means there is a solution to solve the problem, but it is not polynomial time solvable. Like I said here, Hamilton cycle, subsets, traveling salesman problem, these problems and all you might have solved, but they cannot be solved using the polynomial time. They are solved using non-deterministic polynomial time. Such kind of problems where there exists a solution but not a polynomial time are called as NP complete. And undecidable problems are problems where there does not exist a solution to say whether the algorithm gives us a yes or no solution for that problems, or finite or infinite solutions. Such problems falls under NP hard, and here P class problems are problems which can be solved in a polynomial time. Hope you understood, and this is the two topics which you will get for under your portions in 5th module, which you can expect for short notes. And please don't forget to subscribe, like, share and comment. If you click on the bell button, you will get a further notification of my icons, my videos, sorry. Thank you.